tensional stress. So the faults that are going to develop are these faults called normal faults, right? Normal faults, where the hanging wall moves down relative to the footwall. Well, those terms come from miners, because the miners were the first ones to look for fractures in rocks, and these particular fractures are where slip occurs. There's movement across the fault, and fluids can go in there, and fluids may have minerals, so there can be mineralization. So miners would dig mine shafts down here, and you can walk on this footwall, FW for footwall. You can walk on the footwall, you can hang your lantern on the hanging wall. So there would be the definition, footwall and hanging wall. So you can walk on the footwall and you'd bonk your head on the hanging wall. Now in this case, note that I have a marker bed here, maybe like a coal seam or a fossil bed that you can see on both sides of the fault plane here. And what we'd find is that this hanging wall side has moved down. So that's how we're going to call a normal fault. And normal faults occur where hanging walls are moving down relative to footwalls. So all these faults in the basin and range here, you can see in the Owens Valley, the hanging wall moves down. So this is the footwall, because you could walk on this footwall. If you climb Mount Whitney here, you'd walk up a very steep footwall, but the hanging wall has moved down. Same here. Hanging wall move down, footwalls move up. Here's the hanging walls moving down, footwalls moving up, right? So all examples of normal faults. So normal faults pretty much dominate every basin in the basin and range. Now, if we come back to this slide here, is one question I ask is, what could be causing the extension in the basin and range? And geologists think it's probably this mantle upwelling that's occurring. And if we look at the PowerPoint here, under the basin and range, because the crust is thinning due to tensional forces and strike-slip forces, shear stresses occurring out here on the San Andreas Transform, we're seeing thinning here of the basin and range, which allows the asthenosphere to rise, right? And you'll see some decompression melting, and there are quite a number of young volcanic features that occur here as well. But this mantle upwelling, recent papers have also indicated that this mantle upwelling may be responsible for the tilting of the Sierra Nevada. When we start talking about the Sierra Nevada, we'll find that the Sierra Nevada it has a gentle slope on the west side, then a steep escarpment on the east side. And it may be due to this mantle upwelling that's going on in the mantle under the basin and range. Now, in terms of how much extension has occurred, well, there's been an enormous amount. In fact, your book mentions something about a drive from San Francisco to Salt Lake City would be shortened by 2.5 hours if you could undo all the extension. And in Death Valley has experienced tremendous amount of extension. They say it's about 100%. 2 points that might have been a mile apart before are now 2 miles apart, right? And the present rate of extension is about 1 millimeter per year. 1 millimeter. So it continues. One thing I'd like to mention also is there's also quite a bit of strike-slip motion, which is that right lateral shearing motion that's going on out here too. So there's both a component of tensional stress pulling apart, as well as one of strike-slip faulting. So here I mentioned again that most of the basins in the Basin Range and the Mojave are bound by these normal faults. And the structural geology term that we use is one called a horst and graben. So when you hear the term basin and range, geologists are often talking about horst and graben. So a horst would be the uplifted or upthrown block, whereas a graben is the hanging wall that's dropped down, right? So you can see like Owens Valley would be an example of a true graben, and so would Panamint Valley, whereas the White Mountains, Inyo Mountains here would be a horst. But then something unusual happens over here with Death Valley, and Death Valley is said to be a half graben, because between the Panamint Range, Death Valley here, I'll put DV, and the Black Mountains over here, we find that the Black Mountains are a horst, but Death Valley has a fault only on one side. Like the Panamint Valley has faults on both sides, but when there's a fault only on one side, we call that a half graben. You'll see this will lead to a very interesting type of fault called a detachment fault that occurs down over here. So we'll say more about that in a little bit. Now, range front faults, I mentioned those. Normal faults that bound grabens. This extension has resulted in uplift along the Sierra Nevada Front Range Fault System, right? The Front Range Fault System. There's been about 14,000 feet of uplift in the past 4 million years. So that's incredible, right? So we got, here I say 10,000, but it's probably more like 11,000 feet of relief between Owens Valley and the top of the Sierra Nevada. So there's quite a bit of relief. It's a testament to how much these mountains have been uplifting. And the way they're uplifting, we know they're still active today, is because we're going to have earthquakes. And earthquakes are going to cause some uplift. So in the next talk, I'll talk about the great earthquake of Owens Valley, 1872.